So I'm going to share my screen and we are going to go to the next property because the basic property we looked at last time is atomic radius. So today we'll be moving on to the next property, which is metallic character. So we looked at the trends in atomic radius and we answered a few questions. And I love the way Ruth was explaining some of those things. So if you really paid attention to what she was explaining, I'm sure there is something you learned. So we have the trend in metallic character. And of course, when we look at metallic character, we are basically, because remember, in our periodic table, the periodic table is divided into different elements, and those different elements belong to different categories. So in those elements, we have the metals and we have the non-metals. So if we have the metals, we expect that metallic character is a key component that affects the periodicity of those elements. So like we know that on our left-hand side, we have the metals from group 1, group 2, and then of course we have metals in group 3 as well. And then from group 4, we have the metalloids where we have elements that have both properties of metallic and non-metallic. And then of course we know from group 5 to group 8, we have what? Non-metals. So we expect that when we are looking at the periodic table, metallic character as well affects the what? The trend of these elements. And like I've said, you realize that as you move to the right-hand side from the left, because remember, we are still looking at period 3 elements. So if we are looking at period 3 elements, we expect that across the period from left to right, we expect that something to be happening to that metallic character. Is it actually increasing? Is it decreasing? If it is decreasing or increasing, why? So those are some of the questions you should ask yourself, whatever factor we are looking at. So I hope everyone can see my screen. You notice that metallic character depends on how readily these atoms of elements lose their electrons to form cations. So if you remember the topic of periodic table in senior 2, you realize that your teachers looked at how we lose and gain electrons. And you notice that the metals basically lose electrons while the non-metals gain electrons. So when the metals lose electrons, they form positive charges, which are the cations. So for example, sodium, we know that sodium is a group 1 element. Therefore, if it has an electronic configuration of 2 to 8 to 1, it is easier for it to lose this 1 electron than gaining 7 electrons to make it stable. So what happens there is that it's going to lose this 1 electron in its outermost energy level. And once it loses that electron, that means there is readiness for it to lose this 1 electron. And because it has lost that 1 electron, that means its configuration will become 2 to 8. So you notice this configuration is stable compared to the sodium atom. So if we had magnesium, we know that the configuration for magnesium is 2 to 8 to 2. So it is easier for magnesium to lose these 2 electrons than to gain 6 to make it stable. That means if it's going to lose those 2 electrons, we'll have the magnesium ion. And you realize that all these are what? Are cations. So it's giving us 2 to 8. So this configuration is more stable compared to this configuration here. So that is why you find that metallic character is that readiness for those atoms to lose their electrons to form cations or positively charged ions. So, of course, we understand that the increase in atomic size increases the tendency to lose electrons, hence increasing metallic character. So this explains that every time atomic size increases, because remember in our previous lesson, and as Ruth was explaining, you notice that the bigger the atom size, that means it's going to, the atoms in the outermost energy level are not attracted to the what? To the nucleus as much. So that means if the atomic size is big, the what? There is increase in metallic character because it provides that room for these atoms to lose their what? Their electrons. For example, if we are looking at a sodium atom, you realize that the sodium atom has 2 to 8 to 1. So you realize that this one is far apart from the what? From the nucleus, and the repulsion power is stronger than the attractive forces. So if we have this one electron in the outermost energy level of sodium, that means it's creating a larger atomic radius. Therefore, the metallic character increases because that means it provides room for this one electron to quickly be lost than if we had several electrons on the outermost energy level. So because of that spacing between the nucleus and the outermost energy level, it creates that tendency of losing that electron to be higher, which increases the metallic character. Then, of course, we also have to understand that decrease in atomic size decreases the tendency of electrons, hence decreasing metallic character. So you have to take note of some of these. So this one, the spelling is not correct, so I hope you can correct that. So increase in atomic size increases the tendency to lose electrons. And once the tendency of losing electrons has increased, therefore the metallic character also does what? Increases. Then if we have a decrease, the vice versa is true. If we have the decrease in atomic size, that means the tendency to lose these electrons decreases, hence decreasing the metallic what? Character. So those are some of the important things that you need to have at the back of your mind. Hannah's hand is up. Does she have a question?
She didn't have a microphone, so probably she's saying she can't hear you.
Okay, thank you. So I hope at least we are able to grasp those factors. When we increase the atomic size, it increases the tendency to lose these electrons, hence increasing metallic what? Character. And then, of course, if there is decrease in atomic size, by now I understand that we've understood what atomic size is because we'll keep referring to it even in the other what? In the other trends, in the other properties that we are going to look at. So that means there is decrease in loss of electrons, hence decrease in the metallic character. So I want us to identify any 5 metals in the periodic table. Any suggestions on any 5 metals in the periodic table?
Okay, Anne's hand is up.
We have sodium, aluminum, magnesium, lithium, and beryllium.
Okay, that is good. Thank you. Okay, so we have several metals. Even you can choose from the first 20 elements or others. So we have the magnesium, sodium, zinc, iron, aluminum, beryllium, lithium, potassium, calcium. So basically you look at the group 1, group 2, group 3 elements, and then some transition metals that are common to us that we keep looking at. For example, the zinc, the iron, the copper, all those are what? Are metals. And then any 5 non-metals that we know in the periodic table.
We have carbon, nitrogen, oxygen.
Let me just mention the ones in the chat. Someone calling themselves MCs a network. Okay, in that chat, who Anne gives carbon, okay, M gives carbon, Treasure silicon, Leonard gives chlorine, Emmanuel sulfur, nitrogen, argon. Okay. And then who? Fortune Rose says, are semi-metals also non-metals? It's a question she's asking.
She's asking a question.
Yes, that are non-metals also semi-metal.
Rosa, I don't know if it's my network, but I can't hear you properly. Ruth, I think try to get a stable network because we can't hear you. Personally, I can't hear you. I don't know if the rest are able to get what you're saying. Or even you can post in the chat. So there is a list I'm looking at here. It's talking about someone is saying the different non-metals. Okay, yeah, it's here. The non-metals, I don't know if your list has compiled both non-metals and metals because I'm seeing sodium, I'm seeing oxygen, nitrogen, phosphorus, S.4. I don't know what S.4 stands for because if you mean sodium, sodium is not a metal. Sorry, it's not a non-metal. And the symbol for sodium is Na, it's not SO. Maybe if you are trying to mean sulfur, and the symbol for sulfur is simply S. Then we have chlorine, then we have Fe. Fe stands for iron, and iron is not a non-metal, it's a metal. So I hope you take note of that. Those asking the topic is trends in periodic table. And it's the first topic you're supposed to look at in second term if you had covered the senior 4 work for first term. Okay, so when you look at those examples that you've given, because I saw some people giving us examples like sodium, magnesium, aluminium, and many other metals that you mentioned. When you look at those answers that you gave and compare them to the non-metals, I saw some people giving carbon, sulfur, phosphorus, argon, and many others. What do you notice about the positioning of those elements, the metals and then the non-metals? What can you say about their positioning?
Kendo's hand is up.
The metals are positioned in the first three groups, and then the nonmetals are from group 4 up to 7 or up to 8. That is it.
Okay, thank you, Tendo. That is good. I don't know, Ruth, but you're breaking. I can't really get what you're saying. I'm hearing my name, but the rest of the words, I can't hear them. Okay, Richmond, did you want to say something? Because your hand is still up.
Samantha, can you hear me now?
Yes.
Okay, I just had a question on the 5 nanometers where you gave argon. I don't know whether it's right, because if you're looking at metallic character, argon has it has 8 valency electrons, and it's under group 8, and we said group 8 is the group for the inert gases. So I don't know if it's going to be able to lose or gain, to gain if we term it under nonmetals.
Okay, thank you for taking note of that. But you realize in my question, I didn't restrict metallic character to the nonmetals. My question is open. It's identify 5 nonmetals in the what? In the periodic table. Because since it has no ability to lose or gain electrons, what is its metallic character going to be like? You get the point. Because already it's not going to lose, it's already stable. And it's not going to gain because it's already stable. Michael, what is going on? Okay, so Ruth, I don't know if I've answered you.
I think I'll pick on as we move forward.
Okay. Someone had asked for clarity. I don't know. I think I'll expound more as we move on, but I said the way these statements are is how you should get them. If you understood atomic size, that means the bigger the size of that atom, that means it increases the tendency to lose electrons, and hence the metallic character increases, and the vice versa. So that means if I have sodium, I said if we have sodium here, sodium has a configuration of 2 to 8 to 1. You realize that this 1 electron is shielded from the nucleus by these 8 electrons here. That means the attractive force between the 8 electrons and the 1 electron in the outermost energy level is stronger than the attractive what? Forces. Therefore, the outermost energy level is far apart from the nucleus, which increases the atomic size. That is what we explained in atomic size. So that means if that is what is happening in sodium, the tendency to lose this 1 electron becomes higher or increases. So because it can easily lose this 1 electron, therefore there is an increase in metallic character. So that means it has that ability to easily lose the electron because it's far away from the what? From the nucleus, and it's not being attracted by the nucleus. The same thing happens when there is decrease in atomic size, because remember we said the more these electrons are attracted to the nucleus. Like the same way if I have a metal and a magnet, the closer you pull that metal will continue. Actually, you will just find that your fingers as if something is trying to force them to come together between the metal and the what? And the magnet. So it's the same thing when it comes to the nucleus. Once it's surrounded by several electrons, it has that attraction power. And the more you attract something to yourself, that means the distance between you and that thing decreases. But the more there is repulsion, that means you find that the distance does what? Increases. So that is basically what we are looking at. So the bigger the atomic size, the higher the tendency to lose that electron because it's far away from the nucleus. And then it also increases the metallic character. Because remember, we've said metallic character depends on the readiness of that element to lose its what? Its electrons to form cations. I hope the person who inboxed me, you are now with us. And then for Ruth, I was saying that when you look at argon, my question didn't specify according to metallic character. It was just an open question. So I asked 5 metals in the periodic table. That means anyone would give me even a metal that is not in period 3, yet we are looking at period 3, because my question was not specific to a certain thing. Then identify any 5 nonmetals. When you're mentioning nonmetals, that means anything that is not metallic becomes a what? A nonmetal, except for the metalloids. For example, silicon. So those ones, at least you can say that that one is not a nonmetal because it has both metallic and non-metallic characters. But when you're looking at non-metals in generic sense, I can't ask for non-metals and then maybe someone doesn't mention argon. So it wasn't restricting the question to metallic character. It was just an open-end question of which metals do we have, which non-metals do we have. Because this was going to drive me to my last question, which is what do you notice about their positioning? So when you look from group 1, group 2, group 3, you realize that even across the period, if you look at those groups, they are the ones that carry the nonmetals, like I think was it 10 or someone who unmuted and told us. When you look at group 1, group 2, group 3, they are metals. When you look from, apart from carbon, the rest of group 4 elements are metalloids. So you move on to group 5 to group 8, those are nonmetals. So basically that was what I expected us to come up with. So I hope we are together. So when you look at hydrogen, and hydrogen, of course, is a non-metal. It's not among the what? The metals. And we know why it's in group 1. The reason why it's in group 1 is because of its nature. And at least I think you looked at that when you were looking at the periodic table. I don't want to drive into that today. So if we are together up to that point, I want us to move to the next slide. Passion, if you paid attention to Ruthie's explanation before I joined in, you should have an answer to that question. Or if you attended our previous lesson, you should have an answer to that. So let us know in the chat if you attended the previous lesson. If you didn't, then you may have to go back and watch the video because we may not have time to re-explain that. Not in bad heart, but of course to help the people that have been attending. Because if we keep repeating content, it becomes ambiguous. So just let us know in the chat if you are able to attend the previous lessons so that we can know how to help you. Or if you attended the first portion of the lesson, Coach Ruth was really explaining that atomic size. I kept joining in here and there to listen in. So you should at least have a clue. Okay, so after our previous slide, according to the period 3, can someone remind us which elements we have in period 3?
The elements are sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon.
Okay, thank you. So we have those elements. We have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and what? And argon. Remember, when we're looking at atomic radius, amongst these elements, which one has the largest atomic radius?
Endo.
It's sodium.
Okay, do we all agree? So we said sodium has the largest atomic radius in this whole group. Sorry, in this whole period. So that means if it has the highest atomic radius. Remember in our previous slide, we've said if there is an increase in atomic radius, that means there is an increase in the tendency to lose electrons. And that means if there is an increase to lose electrons, that means the metallic character also does what? Increases. So in this case, you notice that sodium, because of its large atomic radius, it has a higher metallic character. So as we go on, you notice that this one has a configuration of 2 to 8 to 1, 2 to 8 to 2, 2 to 8 to 3, 2 to 8 to 4, and so on and so forth. And this one has 2 to 8 to 8. So what do you notice about the tendency to lose electrons as you go across the period from left to right? What do you think is happening to that tendency? Is it increasing or it's decreasing?
The tendency to lose electrons is decreasing.
Okay, that is very good. Ruth, please get a stable network. We can't hear what you're saying. Ruth, we can't hear you. I don't know if you're saying anything. So, I was saying, those who didn't attend the previous lesson, we really can't go back into that because it took us 2 hours to get here. So that means you're going to go to the holistic e-learning platform and you look at that video, then you're able to connect to today's lesson. Even today's lesson will be there, so you can connect from that video to this video and you're able to get all the answers to the questions that you have. Otherwise, we are sorry we can't go back into last week's lesson. Then the other thing, if you follow through, you may be able to punch up some of those things here and there. So I don't know if people are posted in the chat decreasing. For Ruth, I wasn't able to hear you because you're breaking. I don't know if it's on my end only or even for the rest. So here you notice that we have sodium. It has the capability of losing that what? That one electron. And then when you look at magnesium, so as you go across that period, the tendency to lose electrons is decreasing, as many of us have stated in the chart. I am very glad that we've been able to state that out. So you realize that when you move to silicon, phosphorus, these ones start to gain electrons. They are no longer losing their electrons. So that means that tendency to lose electrons is decreasing. And when you go back up there, you notice that across the period, atomic size is what? Is decreasing because there is more attraction across the group, across the period than what? Than repulsion. So that means the atomic size is also decreasing. And because the atomic size is decreasing, that means the tendency to lose electrons, because if atomic size is small, that means these electrons are attracted to the nucleus. So if they're attracted to the nucleus, they cannot easily be lost. So that means the tendency to lose electrons is also decreasing. And if those two are decreasing, definitely metallic character is also decreasing. So that means in this table across the period from left to right, we have a decrease. We have a decrease here. We have a decrease here. And definitely we have a decrease here. So that is what happens across the period when we are looking at metallic character. As atomic size decreases, the tendency to lose electrons decreases, and metallic character also decreases across the period from left to right. I hope we are now together on that point of metallic character. So are we good? Let me get some responses in the chat if we are together. If you have a question, you can raise your hand so I can hear what you have to say. We move on. Are we all good? Okay, thank you, Michael. Thank you, Ruth. Okay, so I think we can now move on to the next property. Okay, thank you, Julia. Thank you, Daniela, Ezra, and Manila. Okay, so we can now proceed. Please ensure that you note down some of these things so that you can go back and review them, or even ensure to watch the video. It will help you understand those things better. Okay, thank you so much for your responses, everyone. So we're going to move on to the next property. And our next property is strength in melting and boiling point. So after understanding atomic size decreases across the period, metallic character decreases across the period from left to right. What is going to happen when we come to melting and boiling point? So here I expect us to at least have a graph book because you're going to quickly try out this activity, and then of course we can discuss thereafter. So I'm going to give us just a few minutes for us to get our graph books, and then you plot the data above. And then if you are through, please raise your hand so that you can tell us what kind of graph you've obtained. So how many minutes should I give us to get this done? They shouldn't be more than 5. So you can suggest the minutes I should give us in the chat, but they shouldn't go beyond 5 minutes because I'll be timing us. Okay, thank you, Divine Face. So those are 5 minutes. So that means we are going to use 5 minutes and we are good to go. So please get a graph paper or a graph book and try out You can plot them on the same graph or on separate ones. It is really up to you, but at least come up with a graph. And please don't just sit back and wait for responses. Try it out, because when we get to explaining, if you've done it, it will make much sense and it will come out clearly when we get to the explanation. So please make sure you're trying out. Chanda, is it possible for you to take a photo of your graph and share it in the chat? I don't know if your phone can do that. Is it possible for you to do that for us? You can just take a picture of your graph and then you can share it in the chat. In the Zoom chat, not in the WhatsApp chat. Please let me know if you can do that. Okay, I can see Owen. This is good. And thank you for using those colors to help us see clearly. I don't know if you're all able to see
Teacher
what is.
Masa?
Yes, please.
No, we can't see anything because we were also using the data you had shared. And now this new window
Oh,
is just a blank
it's blank.
page. Yes.
Okay, let
And
me
it's
find.
also blocking the data.
Oh, okay, let me see. Let me share. So is it back on? Are you able to see now?
Yes.
Okay, thank you. . So we should be winding up. So I hope we had finished copying the data on the screen, because I just want to share this image that one of us shared in the chat, so that at least we can keep referring to it. So if you're not yet through, please just take a screenshot. You will complete that graph. Or even as we explain, you can listen in as you finish up with the plotting. So Aaron, are you able to see the screen?
Yes, teacher.
Okay, so you can see this graph here. I just want to add on a few things before we explain. So after drawing this graph, make sure the axes are labeled. For example, we have atomic number on the x-axis, and then we have the melting and boiling point on the what? In degrees Celsius on the y-axis. So what happens here, down here, where there is atomic number, you always put the atomic number, which is 11, 12, 13, 14, 15, 16, 17, 18. And then when it comes to the, so here you're supposed to have the atomic numbers 11, 12, 13, 14, 15, 16, 17, and then 18. And then when it comes to what you plotted, that's where you write the elements. For example, you'll have sodium here, you'll have magnesium here, you'll have aluminium, you'll have silicon. So I expect that if you had drawn your graph, you put those things as I am saying them. Phosphorus, sulfur, chlorine, and then what? Argon. So that is how your graph should look like, even for both the melting and boiling point. You put sodium here, you put magnesium here, you put aluminium. Okay, depending on how your graph has come out as. So that even when you're explaining, we can keep referring to your graph. So I want someone to explain to us what kind of trend, describe the trend shown by the melting and boiling point, because they are more like similar. So we'll be holding them concurrently. So who can tell us the trend they observe in the boiling and melting points of these period 3 elements? Anyone who has an idea on how they can explain the trend of what is happening? Yes, Hannah. Then Ezra will tell us after.
So there is a general increase from sodium to silicon, after which there is a decrease, like generally.
Okay, thank you. That is good. Ezra?
Yes, thank you, teacher. It is just a supplement. I was
Okay.
inquiring if on these trends that we've labeled sodium, argon, how aren't we allowed to put a key aside, like to differentiate them apart from the color and yeah.
Oh, wow. Thank you for taking note of that, Ezra. So you need to let us know that the melting point, because I think he noted it here. Blue is melting point, red is boiling point. It's very important, especially if you've drawn them on the same graph, to put a key to illustrate which one is boiling point or which one is melting point. Yeah, thank you for taking note. That's very important. So, like Paul said, you realize that there is a general increase from sodium to silicon, and there is a general decrease right from silicon to argon. So when you're explaining a trend, we expect you to tell us what is happening on a general scale. And then, of course, as you give us that general scale, you should be able to tell us why is it happening in that generic way. So if there is an increase from sodium and silicon, why? And if there is a decrease from phosphorus to argon, why is there that general decrease? What causes that to happen the way it does? But the first thing, every time you're explaining these graphs in chemistry, please ensure that you tell us the general trend. Trend means you're telling us how it looks like. Why is it, okay, what does it have? Is it increasing? Is it decreasing? Those kind of terms. So you should be able to explain to us. So you realize that the melting point and boiling point are increasing from sodium to silicon, and then there is a general decrease from phosphorus to argon. So can someone explain to us why do you think it's happening that way? Anyone who can share with us why you think there is a general increase from sodium to silicon, and then a general decrease from phosphorus to argon? What do you think? Did Ruth go for a holiday? I thought she would help me with the people that are raising up their hands.
Teacher, okay, there are two people who have raised their hands. There is Divine.
Okay, you can ask her to unmute so she can tell us.
Okay, so I think that the reason why there is an increase of boiling and melting point from sodium to silicon, it's because like those are the metals, like they have a high ability to lose electrons. And then from silicon to argon, like they are non-metals and they have like they gain electrons.
Okay, thank you, Divine, for
Divine
that
as me.
trial.
Then there is treasure.
Okay. From why there is an increase in the one for metals? I think because the electrons that are in the outermost shell of the metals, they contribute to the metallic bond in the metals. So that's why they that's why the melting and boiling points increase.
Okay, thank you so much, Treasure, for that contribution. So thank you,
Can I also
Devani and
try?
Treasure. Yes, please.
I think there is a general decrease from phosphorus. First of all, we noted that silicon is a metalloid, so it has behaviors of a metal, yet it is a non-metal with its electronic configuration as is it 16, 2 to 8 to 4. Is it? Yes, yes. With its atomic number is 14. So because these are metals and silicon behaving like a metal, we noted before we came to this page that metals have or lose electrons. Now, sodium loses 1, magnesium loses 2, and aluminium loses 3. And since these metals are being, let me take it as they are being boiled or being melted, these electrons will there will be increase in kinetic energy. Thus, the electrons will move or will easily escape. And okay, like uh because okay, they will move off from the so let's say you use sodium, that electron will easily go off because of that increase in kinetic energy. It will lose its direction in the energy level because it's also a free electron. It will leave, and in leaving it will leave it as a cation. Same applies to magnesium, aluminium, and for silicon I'm not sure, but one thing I know, it has behaviors of a metal. That's why for the red, which we call the boiling point, it's slightly lower than the peak we have at aluminium. Okay, that's what I think.
Okay, thank you, Ruth. Though there were very many, but at least I noted some key points in your explanation. That is good. I think I'll enlighten more when I'm explaining. Okay, so Chendo, let's hear from you if I can explain.
Teacher, I think it's because of the mass numbers. Because sodium, magnesium, aluminium, and silicon, let me say they are, although silicon is a metal, but let me take them as metals. We know that metals are hard, and so as their mass numbers increase, also it is so hard for the heat, like to break them, so it takes high boiling points. And then these ones, phosphorus, sulfur, chlorine, and argon, we know that they are non-metals, and so I think it is, okay, may I relate it with mass numbers, that is it.
Samantha, can I correct myself in 1 minute? Which Martha?
Yes, please go ahead.
Yes. So I explained the other way around. These melting and boiling points are high, meaning they take long to boil. Okay, let me use melting. They take long to melt. So the forces that are between let me use Vandal's forces between between the atoms of phosphorus, the atoms of sulfur, chlorine, and argon are are weak. Thus, these electrons are easily lost when subjected to heat or
Ruth, please change your position. I can barely hear what you're saying. You're breaking and we can't hear anything.
Very low. And I
Okay, as Ruth comes back, let's hear from Anne, then Gerald, then we can conclude at that.
Okay, teacher, I think as an element keeps on losing electrons, the attractive forces between its molecules increase, therefore making the boiling point and the melting point to be high. And as it keeps on losing, the attractive forces decrease, therefore making it to have a low boiling point. Then for silicon, the reason why it is on top, it is because it is a metalloid. It has both characters of non-metals and metals, so it's just there.
Okay, thank you so much. That was good. Let's hear from Gerald.
Yeah, good afternoon, everyone.
Good afternoon.
I think the reason as to why metals have a high boiling point is because there are strong metallic bonds that hold their atoms together. So that's the reason as to why they have that high boiling point. The same applies to silicon because it has both the properties of metals and non-metals. That's why it's there. That's my assumption. Thank you very much.
Okay, thank you so much, Gerald. So all those are interesting explanations, but I just want to merge whatever you've said. So just listen in and be able to come up with an explanation that you can actually note down. So first of all, you have to understand that when we are looking at metals, metals have something about them. And remember when we're looking at their their atomic radius, we said atomic radius decreases across the period. So when you come to decreasing across the period, that means the atomic radius is decreasing from sodium to aluminium. So if it is decreasing, therefore, the size of the atom is becoming smaller. And because we know these are metals, that means they have metallic bonds holding them together. And because the atom is becoming smaller, that means those forces of attraction of the metallic forces or the metallic bonds are getting stronger. And if they're getting stronger, therefore, they'll require a lot of energy to boil or melt. So that means when you look at sodium to aluminium, there is a reduction in atomic radius. And because there is a reduction in atomic radius, that means that metallic bonds are stronger from sodium to aluminium, and therefore they will require a higher boiling and melting point. Then we go to silicon. I love the fact that we have identified it's a metalloid. So I'll show us the structure. We are going to look at it in on a search engine. But when you're looking at silicon, silicon being a metalloid has, because when we are looking at the melting and boiling points, we are looking at what bonds, what structure does this given element have? Because we need to overcome those forces that are holding those bonds together, those atoms together. Because for the heat to overcome those different portions, we need to know the nature of that element. So when you look at silicon structure, silicon takes on a 3D structure, which has interlinking covalent bonds. And of course, when you look at covalent bonds, they are also strong enough. They're not stronger than non-metals, but sorry, no, they're not stronger than metallic bonds, but when you look at the structure of silicon, you notice that because it's a 3D and it's made up of covalent bonds, that means these strong covalent bonds require a lot of energy. That is why you find that the melting point and boiling point of silicon is shooting up there because of that reason, because it has those strong covalent bonds and its 3D structure that causes the melting and boiling points to be high. So when we go to the non-metals, most of you have looked at structures and bonds. Actually, all of you in senior, I expect that you've looked at structures and bonds. So because of the molecular structure between phosphorus to argon, you notice that this metallic structure, the molecular structure, the weak van der Waals forces holding those particles together are weak. That means for them, they require less energy to overcome them. Therefore, the boiling and melting points from phosphorus to argon will be low because of the weak forces of attraction between the structures of phosphorus, sulfur, chlorine, and argon. So when you look at the structures of those nonmetals, they are basically made up of that molecular structure, which contains the weak van der Waals forces, which can easily be overcome. Hence, a decrease in boiling and melting point from phosphorus to argon. So, like I said, I want us to look at the structure of silicon. So when you look at this structure, it's showing you a 3D character, because I know most of us have looked at the 3-dimensional figures and we know how they look like. So when you look at this structure here, it is illustrating the network that silicon has. So that means it takes a lot of energy to overcome those covalent bonds, because remember, the silicon is attracted to another silicon, to another silicon, to another, like that. So there is that interlocking of those bonds. So it will require a lot of energy to overcome that 3D structure, and then the what? The covalent bonds that hold those atoms together. So for silicon, you need to focus on the 3D structure with interlocking links between the 3D structure, that is held by the covalent bonds. Therefore, it requires a lot of energy. Then when you look from sodium to aluminium, you're looking at these metals having a reduction in their atomic radius. So that means if the atomic radius is decreasing, that means the metallic bonds are becoming stronger. And if these metallic bonds are strong, they'll require a lot of energy to overcome those bonds. Like I said in the beginning, that when you're looking at boiling and melting points, you're looking at the structure of those elements, and then you're looking at the bonds that hold those atoms together, because it is what will influence the energy to either increase or decrease. Then when you go to phosphorus to argon, you find that these are non-metals. And because they are non-metals, that means they are held by molecular bonds. And these molecular bonds are weak, which we can refer to as the weak van der Waals forces. So if these weak van der Waals forces are that weak, that means they can easily be overcome by less energy. Therefore, a decrease from phosphorus to argon. So you just have to put in that bunch, because when you look at this graph, you notice that here from sodium, magnesium, aluminium, but then there is an anomaly of silicon, which is exponentially high. So you realize that I've explained sodium to aluminium, Then I've explained this anomaly, which seems to be quite high. And then, of course, I've explained this decrease here. So that is how you group those different explanations. If there is a general increase in something, you explain that increase. If there is one that is outstanding, you explain why it's outstanding. Then the ones that are decreasing, you also give a reason why they are decreasing, especially if they are in the same category. Like we've seen sodium to aluminum, they are metals. Then silicon, which is a metalloid. Then we look at the non-metals from phosphorus to argon. So I expect that at least we've been able to pick something from that. If you have any queries, please make sure you're able to rewatch this video before you go back to school so that you can have some of your questions answered. So we are 9 minutes past time, and I hope you're able to read further because we're supposed to look at density, but you can go and read about it. And after understanding these different factors, you can also relate to group 1 elements, and then you're able to explain those different factors. So I'll request someone to pray for us in closure, and thank you all for attending the lesson and for being an active class.
There's Bianca. Bianca, you have your hand up.
Okay, I'm seeing 2 hands up. Bianca, are you praying for us?
Yes. Let's humble ourselves. Lord Heavenly Father, we thank you for this lesson. Thank you for all the information that we've taken in. Thank you for the ability to be here, Lord Father. Thank you for our teacher and the co-hosts, Lord Father. Thank you so much. We don't take it for granted, and for those that haven't understood, for which you may give them the capability and the lack of not only to the work and doing it, Lord Father. Thank you once again for the teachers, and we pray you may continue to bless her and the co-host as well, everyone that has helped in the lesson. And thank you for those that were able to attend, and those that weren't, Lord Father, pray they may attend next time. In your mighty name I prayed and believed. Amen.
Amen. Thank you so much, Arinda. Thank you everyone for your active participation, and I wish you the very best. Remember, our target this term is for you to get A+ in chemistry. So make sure you give it your best, do what you have to do. And I believe every one of us can make it if we choose to. So it's a choice that you have to make. Otherwise, have a lovely time and God bless you.